So at an unbiased PN junction, the diffusion current will be equal to the drift current. And keep in mind that diffusion current is due to majority charge carriers. Drift current is due to minority charge carriers. Okay. And as the name suggests, unbiased means we are not favoring any particular process. Fine. Suppose we bias the PN junction. Biasing means favoring a process. Now, how do we favor any of these processes? Diffusion or drift? You can do that by adjusting the strength of electric field in the depletion region. If you make the electric field weaker, okay, now due to that electric field only, there is a potential barrier between the N side and the P side, and the electrons won't have sufficient energy to jump over that barrier. If you make the electric field weaker, the potential difference between P side and N side will decrease. If you can decrease the potential difference, then electrons will easily be able to jump over from N side to P side. So what will you be doing? If you weaken the electric field in the depletion region, you will be favoring diffusion. Okay. And if electric field is weakened, see what is the electric field doing? It is making or it is creating drift current. If you make the electric field weaker, drift current will decrease because the field won't be strong enough to bring the electrons back to the N side or push the holes back to the P side. But diffusion will keep happening. So if you weaken the electric field in the depletion region, you will be favoring the diffusion process. Okay. And you will be opposing the drift process also at the same time. On the other hand, if you strengthen the electric field, then what will happen? The potential barrier will become even higher. It will become very difficult for electrons to go from N to P or for holes to go from P to N. So diffusion will become very difficult, whereas drift will increase because if you strengthen the electric field, the field will bring more electrons back from P side to N side, or it will push more holes back to the P side. So if you strengthen the electric field in the region, depletion region, you will be favoring the drift process. Okay, so that is how we can bias a PN junction. So first is PN junction under forward bias. It's very important to understand the mechanism, what exactly happens at the or what exactly happens to the electrons and holes. Okay, Pratin is asking if there is increase in drift, then will there be actual current through the diode? Okay, just wait for 10 minutes. We will discuss that. Okay, reverse current and all. Right. So it is clear that this is the P side, this is the N side. Now, if you want to make the PN junction forward biased, okay, forward bias means favoring the diffusion process. How do you favor the diffusion process? By weakening this electric field. So you will have to create another external field which is opposite to the existing one. That's all. And you can do that by applying a voltage across the PN junction. Suppose you apply a voltage like this, where P is kept at higher potential and N is kept at lower potential. Okay. Let's assume a switch for now. Let's say it is still not switched on. Okay. So as of now, the junction is unbiased. There will be a certain amount of electric field. Okay. The moment you close this switch, what you will be doing is you will be creating an electric field. The battery will be creating an electric field opposite to the existing electric field. Okay. So suppose the switch is closed. What will happen? The electric field in the depletion region will become weaker. In an ideal case, it totally disappears. Okay. Assume the net field in the depletion region becomes zero altogether. See, the existing field was from N side to P side. Now you connected or you made P side at higher, you kept P side at higher potential compared to the N side. So an additional field will get created from P to N. Existing field was from N to P. These two will oppose each other. And if you use a battery which is strong enough, you will be able to cancel the electric field altogether in the depletion region. Okay. Now, if electric field is not there in the depletion region, then there will not be a potential barrier. Or if electric field in the depletion region becomes weaker, the potential barrier will become weaker. Now, if potential barrier becomes weaker, basically what happens is something like this. More electrons will be able to jump over from p side to n side. Now, if that electric field is not there, or if that electric field is weaker, basically the depletion region becomes narrower. Okay, let's assume it's not completely cancelled. The electric field is not completely cancelled, but let's say it has become weaker. So what happens is narrowing of the depletion region. That's the first thing that you will notice. Now there is a very weak electric field. Okay. So conduction electrons will now be relatively easily able to jump over the potential barrier and go to the p side. Now listen, they don't just go to the p side and settle there. There is a battery. What is the job of a battery generally? To pull electrons from one side and deposit them on the other side. And from which side does it pull electrons? It pulls electrons from the positive terminal. Okay. So battery pulls electrons this way. And then it pushes them out on this side or deposits them on this side. Okay. Now electrons which diffuse from n side to p side, not all of them will combine with holes. Only if the electron loses energy, it will settle down in a hole. Otherwise, it will keep moving around on the p side. It's a conduction electron, right? When it goes from N to P, it doesn't definitely fill a hole. It will still be free to move around. Most likely, it will be free only. It is less likely that it undergoes some collisions, loses energy, and settles in a hole. So the electrons which go from N to P will be pulled by the battery. Okay. As a result, what will happen? Electron circulation will happen. It will get pulled by the battery and it will get deposited back on the inside. And if it is deposited back on the inside, it will again participate in circulation. Okay, that is how a current is created. Right? And this is not the only way current is created in forward bias. Holes also diffuse from p side to n side. Okay? Electrons diffuse from n to p. Holes also diffuse from p to n. There is current due to that as well. Now, if an electron goes from N to P, electron is negatively charged, means current is from P to N. If a hole goes from P to N, hole is positively charged, means current is from P to N. Okay. So whether it is electron diffusion or hole diffusion, current is from P to N. And in forward bias, you favor diffusion. Okay. Now see, the electric field has become very weak. So that electric field in the depletion region won't be able to bring many electrons back from P to N. Okay. So drift will not be that strong, but diffusion will be very strong. As a result, there will be a net current through the PN junction. And current will be from P to N. Okay, this is mostly due to, or this is due to diffusion. Drift current is almost zero, you can say. In fact, if the battery voltage is strong enough to make the electric field zero in the depletion region, drift current will completely become zero. Okay, only diffusion current will be there. Now comes the important point. Diffusion happens due to movement of majority charge carriers. Okay, so there are many charge carriers which participate in this process. Therefore, the current that you see, okay, under forward bias favors diffusion process. The current that you see under forward bias will be a significant current because there are many charge carriers to participate in the diffusion process. Okay, therefore, under forward bias, current through the junction will be significant. Okay, it will be from P to N and will be significant. In fact, stronger the voltage you apply, okay, like if you increase the potential difference between P and N, see in forward bias, P is kept at higher voltage than the N side, higher potential than the N side. So if you increase that biasing voltage, the current will increase, okay, because the battery will be pulling more and more electrons. It will be circulating electrons faster, you can say. Okay. So forward current will keep on increasing as you increase the battery voltage. But you can think of it like this. See, initially under unbiased condition, drift and diffusion were equal. Okay, they were in equilibrium. I mean, the PN junction was in equilibrium. Now, if you apply a forward biasing voltage, okay, forward biasing voltage is called positive voltage, and study the current that results in the PN junction, okay, through the PN junction. When no forward bias voltage is applied, there is no effective current. This is the net current. So when biasing voltage is not applied, there is no net current through the junction. Diffusion and drift are balanced. When you apply a biasing voltage, you will be favoring diffusion. Now, if the applied voltage is very small, there won't be a significant what do you say? There won't be a significant decrease in the electric field if the biasing voltage is very small. Now, if there is no significant decrease in the electric field, there will not be significant increase in the diffusion process. Okay. For current to be significant, there must be a lot of electrons diffusing from N to P and lot of holes diffusing from P to N. For that to happen, the electric field should decrease significantly. So, for small values of biasing voltage, okay, forward bias voltage, you won't see much current through the junction. It will be very small. Okay, but when the electric field decreases significantly, you will see a significant rise in the current. So the behavior will be like this. Up to a certain voltage, there is no significant current through the junction, even if it is forward biased. Okay, that voltage is called knee voltage. Okay, usually, like see, the knee voltage beyond which you get significant current depends on the material with which the PN junction is made. Okay, the elements with which you have made that junction. Usually, for a silicon based PN junction, this is about 0.7 volts. Okay, for a germanium based PN junction, it is about 0.2 to 0.3 volts. Okay, approximately 0.2 volts. Beyond that forward bias only, you will see significant current through the PN junction. Okay. Now you can clearly see that the current versus voltage graph is not a straight line passing through the origin. If it's not a straight line passing through the origin, you cannot say V is equal to IR. Okay. So a PN junction under forward bias does not obey Ohm's law. Okay. Important point. It does not obey Ohm's law because the current versus voltage graph is not a straight line passing through the origin. Okay. But you can see that once the voltage is greater than the knee voltage, the graph is almost a straight line. Okay. In that region where the graph is a straight line, if you choose 2 points, okay, straight line has a constant slope, no? Between these 2 points, there will be a small change in potential, delta V. Okay, small change in voltage, I should say, small increase in voltage. When you increase the voltage, you can see that the current through the junction is increasing. Okay, so an increase in voltage results in an increase in current, delta I. This ratio, delta V divided by delta I, is what you call as dynamic resistance of a PN junction in forward bias. Fine. So for PN junction, current flowing through a PN junction, we define something called dynamic resistance. So once the voltage is beyond the knee voltage or greater than the knee voltage, you will see significant current through the PN junction. For a small change, for a certain change in voltage, there will be a certain change in current. That ratio is what you call as dynamic resistance. So if they want to ask you questions based on this, they will give you a proper graph of the current versus voltage and ask you what is the dynamic resistance. So in the graph, you will have coordinates. You'll be able to see the coordinates, x coordinates, y coordinates. So you choose any two x coordinates. The difference between them will be the change in voltage, and the corresponding y coordinates, the difference between them will be the change in current, and you can calculate the dynamic resistance. Okay. So why is there significant current in forward bias? Because forward bias favors diffusion, and diffusion is due to majority charge carriers. There are a lot of them which participate in this process. Okay. And remember, in forward bias, you will be weakening the electric field in the depletion region. If the electric field is weakened, the potential barrier is lowered. Fine. Next, reverse bias. Reverse bias favors drift. Okay. Now, how do you favor drift? You can favor drift by strengthening the electric field in the depletion region. So basically, you need to create additional electric field which supports the existing electric field. Just a moment. Right. If you want to support the existing electric field, you bias the PN junction like this. You connect positive terminal of the battery to the N side and negative terminal to the P side. So effectively what you will be doing is you will be creating additional electric field directed from N to P. And if you create additional electric field directed from N to P, what it results in is widening of the depletion layer. And the electric field will now be much stronger than what it was before. It will still be directed from N to P, and it will be stronger in magnitude. And if electric field is stronger, basically the potential difference between N side and P side will be stronger. So you will increase the potential barrier. So if potential barrier is increased, or if this electric field is made stronger, what you will effectively be doing is you will be making it very difficult for electrons to go from N to P. Means you will be opposing the diffusion process. But by making this field stronger, what you will be favoring is the drift process. What happens in drift? The electric field brings electrons back to the N side, pushes holes back to the P side. But from where? In the depletion region itself. See, the region from here to here is the depletion region. That's the region in which the electric field is present. Fine. In the depletion region, why is it called a depletion region? Because there are no charge carriers there. Means there are no conduction electrons or holes present. See, electrons are there, material is there. Fine. But they are in valence shell. They are not in the conduction shell. Fine. So all the electrons in the depletion region are in the valence band. They are not free to move around. And this electric field cannot disturb the valence band electrons. Only those electrons which are free to move around, means only those conduction electrons can undergo drift due to this electric field. So it can't do anything to the valence electrons. The valence electrons are participating in bonds. They will stay in bonds. Occasionally, electron hole pairs get created. Okay. Electron hole. Like suppose an electron jumps out from the bond. That happens all the time, no, in intrinsic semiconductors. It doesn't happen at many places, but it happens all the time. Okay, at a few places here and there. So suppose an electron jumps from the valence band into the conduction band. Then this electric field will pull that electron back to the N side, and it will push that hole to the P side. Now, if it is created on the P side, let it be there itself. Okay. So the electron generated, the conduction electron generated on the P side will get pulled back to the N side. if it is generated. Okay, which will happen, but it happens very rarely. I mean, very less frequently, I can say. Same thing here. There is some depletion region on the N side also. No? Suppose an electron hole pair is generated there. What will this electric field do? It will push that hole back to the P side. Okay. So in reverse bias, okay, by keeping N side at a higher potential than the P side, you are making that electric field in the depletion region very strong. But that electric field is actually helpless. It cannot result in much current. Why? Because in the depletion region is called depletion region because there are no charge carriers. Okay. So even though there is an electric field, there is nothing for it to do. There are no charge carriers for it to uh, exert a force on. Occasionally, if any charge carriers appear, okay, then they will definitely feel the force of that electric field and they will definitely participate in the drift process. So in reverse bias, drift is favored. So drift or diffusion is opposed to drift is favored. Both things you have to consider. Okay. So drift is stronger than diffusion. But drift is due to minority charge carriers. Fine. They are not always there or they are not there in large numbers to participate in this drift current. Occasionally, whenever an electron jumps from valence band to conduction band, that will participate in the drift process. Therefore, reverse bias current is negligible. Pradyum, does this clear your doubt that, okay, your question was if there is increase in drift, will there be actual current through the diode? Okay. See, there will be current, but it's a negligible current. Very, very less compared to what you see in forward bias. Because forward bias current is due to majority charge carriers. Reverse bias current is due to minority charge carriers. Okay. And the name itself suggests they are very less in number, so they won't result in significant current at all. Okay. In an ideal case, we assume reverse bias current is zero. Even if you, okay, a larger blockade in reverse bias. Blocking of what? Anyway, you yes, obviously. See, the diffusion process is opposed, no, very strongly. Okay. Yes, you are increasing the potential barrier. So electrons will not be able to jump from here to here. And the battery also does not favor that. Fine. So diffusion is completely opposed, you can say. Or very rarely an electron may go from N side to P side also, but it won't result in a significant current anyway. So diffusion current is very less. Drift current will dominate, but drift current naturally is less because it is due to minority charge carriers. Therefore, the net current will be very less in reverse bias. It is negligible. In an ideal case, we take reverse bias current to be zero. But it's important to understand another thing here. Okay, let me write this first. In reverse bias, potential of the N side is greater than potential on the P side. That means drift current will be greater than diffusion current. And because drift current is due to minority charge carriers, it is negligible. Okay. Even if you increase this reverse bias voltage, you won't see significant increase in current. There will be a slight change, but it will still be very small compared to the forward bias current. So in an ideal case, you can say the reverse bias current through a PN junction is zero. In a real case, it will be in microamperes. Okay. A very, very small current will be there. Okay. Now, whether it is forward bias or reverse bias, fine. Generally, whenever current flows through a material, current is what? Flow of charges. Whenever electrons flow through a material, they'll definitely undergo collisions. They will definitely produce heat. Okay. Now you consider forward bias. As you go on increasing the forward bias voltage, the current will go on increasing. Fine. Now, as current increases, the heat produced will also increase. Electron collisions will increase. So it will generate more and more heat. And the semiconductor material with which the PN junction is made will only be able to withstand heat up to a certain extent. Every material has limits, no, up to which it can withstand the heat. So what happens if you increase the forward bias voltage too much? There is a chance that the current increases to such high levels that the material gets damaged, that the semiconductor or the junction gets damaged. Okay, so that could happen. You can't allow forward bias current is significant, that's fine. That doesn't mean you can increase it to whatever levels you want. Okay, because every material has limits. There will be a limit to the voltage that you can apply in forward bias. Beyond that, it will result in too much current, which the material won't be able to withstand, and the junction will get damaged. Okay, it will get burnt. So there is a limit to the forward bias voltage that you can apply. There is a limit to the forward bias current that can be produced in a or through a PN junction. Reverse bias. Now in reverse bias, there's no current, so it appears safe. Okay, like it appears as if the PN junction is not going to get damaged. But understand what happens in reverse bias. Why is there no current in the first place? Because reverse bias current is due to minority charge carriers. Fine. Minority charge carriers are not always present. They get generated whenever there is an electron jumping from valence band to conduction band. Okay. Now, this electric field in the depletion region is ready to bring the electrons back to the n side whenever they are generated. Fine. What happens if you increase this reverse bias voltage too much? If you strengthen the reverse bias voltage, you will be strengthening the electric field. If the electric field strength increases, goes on increasing, at one point, what the electric field can do is it can pull the valence electrons into the conduction band. Okay, now in dual nature, we had discussed something called field emission. If you apply a strong enough electric field, you can pull electrons out of the material. And in second chapter, potential and capacitance itself, we had discussed something called dielectric breakdown. Okay, capacitors have a voltage limit. Okay, because the dielectric between the plates of the capacitor has a certain limit up to which it can withstand a potential difference. Okay, even lightning happens due to dielectric breakdown. Lightning is nothing but transfer of charges between the earth and clouds. Between earth and clouds, there is air present, which is an insulator. But if the potential difference becomes very strong, the air becomes a conductor. Why? Valence electrons go to the conduction band. And it facilitates transfer of charge between the cloud and the earth. Same thing can happen in any material, including the semiconductor. So if you strengthen the reverse bias voltage too much, the electric field in the depletion region will become so strong that it will start pulling out valence electrons and bringing them into the conduction band. Now, when a valence electron jumps into the conduction band in the depletion region, it will get pulled by the electric field. Okay, it will have to participate in drift. So what happens? Let me just copy this. Right. When the electric field becomes too strong, I'll remove the field lines just for us to be able to visualize what happens more clearly. There will be too many conduction electrons, and whenever there is a conduction electron created, automatically hole will also get created. So there will be too many electron hole pairs generated like this. Then this electric field will pull those electrons to the n side, it will push the holes to the p side. This will result in a large current, sudden large current. Now electrons are going from P to N. Negative charge going from P to N means current going from N to P. Holes go from N to P. Positive charge means current goes from N to P. So drift current will start becoming significant. So basically what is happening here, if you strengthen the electric field too much, the valence electrons are being pulled into the conduction band, means the insulator is becoming a conductor, or you can say the semiconductor is becoming a conductor. Okay, it's possible. Insulators itself become conductors when the potential difference is too large. Why can't a semiconductor do that? It can. Okay, it can happen with a semiconductor also. So beyond a certain reverse bias voltage, the electric field becomes so strong that the semiconductor becomes a conductor, and then it will result suddenly in a very large current. Okay, that is called as breakdown of the semiconductor or breakdown of the PN junction. It will lose its semiconducting properties, it will become a conductor now. Okay, and it will result in a sudden strong reverse current, and that reverse current will be so strong that it will usually damage the PN junction. It will generate a lot of heat and usually damages the PN junction. That's why it's called the breakdown voltage, and resulting current is called the breakdown current. Okay, so in reverse bias, the current versus voltage graph okay, reverse bias voltage is called negative voltage. When the voltage is zero, the current is also zero. Fine. We take voltage on the x-axis, current on the y-axis. Reverse bias current is basically drift current. Okay, and it's called negative current. Now, for small voltages, for small reverse bias voltages, the current will almost be zero. There will be a small reverse bias current, but it will be very close to zero. Even if you increase the reverse bias voltage, the current won't increase much. Okay, but there is this voltage called the breakdown voltage, right? Denoted by VBR. Up to that voltage, you can increase. You won't see significant current in reverse bias. But once the voltage becomes reverse bias voltage becomes stronger than the breakdown voltage, you will suddenly see a large current flowing through the PN junction. Okay, and that usually results in damage of the PN junction. That voltage is called breakdown voltage. So in forward bias also there are limits to current. In reverse bias, that current which is enough to damage the junction will be produced once you cross the breakdown voltage. Okay. So basically, breakdown voltage is the maximum reverse bias voltage which the PN junction can withstand or bear. Okay. If the reverse bias voltage is stronger than this, valence electrons start moving to the conduction band, semiconductor becomes a conductor. Okay, and it will result in a large reverse bias current, which will most likely damage the PN junction. Okay, so understanding this process is important. Why there is very small current in reverse bias and why it suddenly increases when the voltage crosses a certain limit. Fine. So this property of a PN junction to allow current in one direction, okay, that is the forward direction. It allows current from P to N easily if you bias it in the correct manner. And to stop current in the opposite direction, when you do reverse bias, the current is negligible. Okay, provided there is no breakdown that happens. Okay, so we'll discuss everything under that condition only. Suppose breakdown is not happening, PN junction allows current from P side to N side, but it does not allow current from N side to P side. This property of PN junction is what makes it very useful in making semiconductor devices. Okay, in fact, the PN junction itself allows current in one direction, doesn't allow current in the opposite direction. A device which can do that, okay, a device which can allow current in one direction but stop current in the opposite direction is called a diode. Okay, so the PN junction itself is effectively a diode. And the standard symbol for diode is this. A triangle and a straight line with two terminals. One terminal connected to the triangle, one terminal connected to the straight line. Triangle side is the P side, straight line side is the N side, and the triangle looks like an arrow, which in fact tells you the direction in which it can allow current. Okay. See, if the diode is biased properly, if the PN junction is biased properly, it can allow current from P to N. Okay. In reverse bias, it does not allow current from N to P. So there's only one direction in which it allows current, and that's from P to N, that is indicated by the arrow. Okay. Consider this situation. Now, when does diode allow current? In forward bias, it allows current. Means in a circuit, when you place a diode, if you see that the P side is going to be at a higher potential than the N side, okay, then you can say that there will be current through the diode. Now, let us discuss ideal diodes and real diodes. Diode allows current in one direction, does not allow current in the opposite direction. No. An ideal diode simply behaves like a wire. Okay, means it allows current freely like a wire does under forward bias. You can ignore its resistance. You can ignore the potential difference across the diode. Okay, you can think of it as a wire. If you are given any resistance, then it means they are talking about a real diode. You include that resistance in the equations. Okay, we'll solve problems, you'll understand. And under reverse bias, it behaves like an open switch, absolutely no current at all. Okay, this is how an ideal diode behaves. A real diode, see, real diode will offer some resistance. In reality, every material has some resistance, okay, to the flow of electrons. So under forward bias, there will be significant current in a real diode. But what happens? There will be a small potential drop. See, current flows from P side to N side, okay? P side, let's call this point as X, and N side, let's call this point as Y. When current flows from X to Y and there is a resistance in between, okay, there will be a small potential difference even in forward bias. Okay, so there will be some electric field still existing in the depletion region. So small potential difference exists across the diode. In case of a silicon diode, this is about 0.7 volts. In case of a germanium based PN junction diode, this is about 0.2 volts. That potential difference will be there. Okay. So it doesn't behave like a simple wire. You have to consider 2 points, one point to the left of the diode, one point to the right, between which there is some potential difference. Okay. In reverse bias, you still consider it as open switch itself. Okay, wait. Small potential difference exists across the diode in forward bias. Basically, we are considering its resistance. In reverse bias, again, you treat it as an open switch only. Infinite resistance. Fine. Let's solve some problems based on this. Suppose this is a 5-volt battery and there is a 2 ohm resistance and a diode in this circuit. There's a single loop. Assume the diode is ideal. Okay, first case. Tell me, is this diode forward biased or reverse biased? How do you decide that? You will have to, what can you say? Think of it as a resistance first. Okay, whether it's real or ideal, think of it as a resistance. Try to find out in which direction current is going to flow through that resistance. Then indirectly you will be finding out in which direction current may flow through the diode. And you know that current is allowed only in one direction through the diode. So first think of it as a resistance, find out the direction in which current is going to flow, and then you see whether diode will allow current in that direction or not. That's how you determine whether it is forward biased or reverse biased. So fine, we need not think much in this case. This is definitely forward biased because current will flow like this. Okay, so current is going to flow from P side to N side in this through this diode, so it is forward biased. Now, if it's an ideal diode, there's no potential difference across its ends. So it's simply like a wire, as I said. So you treat it as a wire, then how much will be the current? I is equal to V by R. 5 divided by 2, 2.5 ampere current will flow through it. Okay. Suppose it was a real diode. And in case of a real diode, they will mention in the question how much voltage exists even under forward bias. Okay. So suppose it's a real diode, silicon based, where forward bias potential difference is 0.7 volts. Okay. Derive the current. Solve this, both of you. Okay. See, the diode is forward biased, so it will allow current. Now, we applied a voltage of 5 volts. That's fine. Current will flow through this diode, but as current flows through the diode, now you will have to consider its resistance as well. And it is told to you that the forward bias voltage across the diode is 0.7 volts. Means when current is flowing through it in forward bias, there will be a potential difference of 0.7 volts across the diode. Now, across the diode, if the voltage is 0.7 volts, then what will be the voltage across the resistor? Remaining voltage, 5 minus 0.7, 4.3 volts. And that is what results in current. Then the current here becomes 4.3 voltage divided by resistance. That becomes 2.15 ampere. So this is how you deal with real diodes. First check whether it is forward biased or reverse biased. If it is reverse biased, no current. If it is forward biased, then you assume that forward bias voltage exists across the diode. Remaining voltage you have to distribute to the remaining parts of the circuit, okay, of the branch. Next. Okay, try this problem. The net resistance of the network as shown in the figure. Okay, and they have given you the terminal voltages also, minus 6 volt on one side, minus 8 volt on the other side. Now see, the voltage on one side is minus 6 volt, the other side is minus 8. So effectively this is higher voltage and this is lower voltage. Fine. There are three resistors, two of which have diodes along with them. Okay. Now 15 ohm resistance, current will definitely pass and it will pass this way. Okay. 10 ohm resistance. Now think of this diode as a resistor. So there are two resistors in this branch. Left side is positive, right side is negative. So current goes from left to right. Now when I say positive, negative, I mean one side is at higher potential compared to the other side. Okay. Usually that is what positive negative means. So current can flow from left to right. And this diode does allow current from left to right. So this is forward biased. Okay. In the last branch, if you see, think of the diode as a resistor. Current tends to flow from left to right, but that would mean reverse bias current through the diode, which it will not allow. So this last diode does not allow current. There won't be current flowing in that last branch at all. So you have to consider this situation like this. You can think of this diode as a wire, fine, but you will have to think of this diode as an open switch. That's all. The diodes are ideal. Okay, if they don't mention anything in the question, you will assume they are ideal diodes. Then what will happen? There will be current flowing through 15 ohm and 10 ohm. The 5 ohm resistor is effectively not part of this circuit. So how much is the effective resistance? 15 and 10 are in parallel. Then the effective resistance will be R1 R2 by R1 plus R2. 150 by 25, 6 ohms. Okay, next question. Okay, in this question, they have given a battery, two resistors, and two diodes. And they mentioned that one diode is made of germanium, the other is made of silicon. So the intention is to uh, like indicate that these are real diodes. Now, a germanium diode in forward bias has a voltage of 0.2 volts across it, and silicon diode has a voltage of 0.7 volts across it. Okay, so by assuming, in case you are sure that they are forward biased, you have to assume these voltages across the diodes and find out the whatever is out. They are asking you voltage across the load resistance, so they want you to find out the potential difference across this one. Okay, try this, both of you. Fine. Since the diodes are forward biased, there will be current, and these voltages will appear across the diodes. 0.2 across the germanium diode, 0.7 across the silicon diode. Out of the total 15, if you remove 0.2, 0.7, you will be left with 14.1 volts. Therefore, the potential difference from this point to this point, means across the combination of the two resistors, is 14.1 volts. Now you need potential difference across the load resistance of 2.5 kilo ohms. Now there are two resistors basically, 1.5 kilo ohms and 2.5 kilo ohms. And you can see that they are in series with each other. So in series, when a certain voltage is applied across a branch, yeah, the voltage gets distributed in the same ratio as resistors. We know V is equal to IR. So V1 is to V2 will be R1 is to R2 because series has same current. Okay. So the total voltage is 14.1 volts. You have to split it in the ratio 1.5 is to 3.5 or 2.5 means you have to split it in the ratio 3 is to 5. 3 is to 5 means totally 8 parts. So 3 into 14.1 by 8 will appear across the 1.5 kilo ohm. 5 into 14.1 by 8 will appear across the 2.5 kilo ohm resistance. Okay, kilo ohms. And 5 into 14.1 divided by 8. 8.8 volts. Okay, 8.8125. Fine. See, actually in the question they are supposed to mention, okay, how much voltages you are supposed to take. Usually we take these. In the actual options given for this problem, there is 8.75. Okay. There is 8.75, 8.5, 9, and 14. Okay. Which makes it slightly confusing. Out of these options, which one will you choose?
Sir, 8.75.
Why? Because it is closest.
Yes, sir.
Maybe. Actually, they have to give those voltages. Fine. Right, right. So in this case, the answer will be 8.75. Now, if it is 8.75, that means this share, the share of these two, 0.2, 0.7 is slightly greater. Okay, let it be. If I had they given those voltages, we could have calculated accurately. Fine. Right. So today we discussed about PN junction under forward bias and reverse bias, how it behaves as a diode, and how to solve simple questions based on diodes. Fine. Next class, we'll talk about how a diode can be used as a rectifier. Okay, we'll discuss what is rectification, how a diode can be used as a rectifier, and there's something called a Zener diode, a special purpose diode, Zener diode, then photodiode, LED, solar cell, and after that, logic gates. Okay, thank you all. We'll continue in the next class.